Okay, so today what I want to talk about in this section is analog versus digital. And I think of those words like, they sort of come up. I think of it as sort of like the word entropy. Like, it's hard to know exactly what they mean. So I really like today's lecture, this section, because I can show you how those things really work. And in a way, I think it is something that every day of your life from here on out, you'll know something about how audio or all these things that are just very ubiquitous, how they work. So let me get lower the screen down here. So I'm going to start off, really the question I want to address is what is analog versus digital? And digital is how things work in the computer, so that's where I want to get. So I'll start off with analog. So the world is basically analog. And what does that mean? Well, the simplest case, and the running example I'm going to use today is sound. So what does sound look like? How does sound work? The sound of my voice or music or something. So sound is actually just pressure waves in the air, just little minute increases or decreases in pressure. And inevitably, it's described as traveling out through the air like if you threw a pebble in a pond and you sort of saw the waves traveling out. So here's my just made up example of what a sound wave might look like. It turns out many of the sounds that we're used to in day-to-day life do have this kind of repetitive pattern. And so that'll come up. So I'll use here's a slightly better example. So how does a violin work? No expense has been spared on this artwork. Yes, question? Is material on... Oh, I'm sorry. Yeah, I haven't put this on the webpage yet. I will after class, but there's please, yeah, sorry. So a violin, so a violin is just a musical instrument. You can play it, but how does that work? Well, the way the violin works is that there's these strings, and they're attached to this hollow wooden body. And as the bow is drawn across the strings, they're metal and they're under tension, and they vibrate at a sort of repeating frequency. And really, the gist of it is that it vibrates the wood of the violin. And so the wood will flex out a little bit and flex in a little bit. And so it's sort of like a drum, right? You can think of it as kind of bumping up and down. And what that does is it creates little pressure waves in the air. And so those travel out in all directions. And eventually, so there's the signal in the violin. I'm drawing it as like this little wave. It's going a half a millimeter up and a half a millimeter down. And then that translates into the air, where it's going out as these little pressure waves. And the thing about analog is that the shapes are the same. So that on the violin, if it kind of went up a little, down a little, up, whatever. And we could have sounds with different sharpnesses and different frequencies. And then that is reproduced in the air, basically. So it's traveling out in the air. And eventually it gets to your, here's the list. Here's you. And you're listening. And in your ear, there's the little eardrum, right, which is very much like a drum head. And the air pushes against it. And so it pushes it in a little bit, out a little bit. So that, partly it's just my low-quality explanation of how violin sound works. But also that's very analog. That you had something on the violin, right, in wood, basically. And then it translates into some other medium, into air. But you sort of keep the shape. And it travels in the air for a while until it gets to your eardrum. And then again, in the eardrum, the shape is preserved. That is the fundamental quality of analog processes. You're sort of jumping from step to step, but keeping the shape. So to show you how this works, I want to do some demos and experiments and stuff. I'm going to use a device called an oscilloscope. A sure sign that the nerds are near is if there's an oscilloscope. An oscilloscope's a really neat, in my opinion, really neat device. And it very much gets at this idea of analog. What an oscilloscope does is it takes in electricity on a pair of wires. And it just looks at the wires. And it observes the signal of voltage kind of going up or down over time. It looks at that signal, and it reproduces it on screen. So you can, something which is very abstract, right? I gesture my hands, and I say, well, there's the sand coming out of the violin. But it's just hand waving. The oscilloscope makes it real. It takes a signal out of the wire, and it draws it, makes something visual. And I think we're very visual creatures, and so to me the oscilloscope is kind of amazing. Or, it's very, very handy. These things have been around actually for a long time, since I think the 1930s. And the one I'm going to use today, if I switch the screen here. This is actually a digital oscilloscope hooked up to my computer just because it makes it easy to display stuff. But it is, at the end of the day, an oscilloscope. So this is the oscilloscope output. Right now, what it's showing is nothing. Oh, actually, I'm sorry. Let me switch back and explain a little bit more how this works. So the way the oscilloscope works is it grabs the signal off the wire, and it draws it. And the way the oscilloscope I'm using works is it leaves the signal up there for maybe a tenth of a second. It freezes it, and then it grabs another signal off of here, and it puts that one up. So it doesn't quite track what's on the wire in real time. There's maybe a half-second delay, just because that's the way this one works. So what I've got for my demo here is I've got this, and as will become obvious, I'm no musician, but I have this synthesizer hooked up. And so the synthesizer is hooked up to the speakers, so I can make sounds and kind of play around with them, but it's also hooked up to the oscilloscope. So what is this, like 2 of the 5 senses, right? So you can hear it, but you can also see it. And so then we can talk about what is a wave, what is a signal. Alrighty, so this is where the complicated demo, this is where I guess I need to appeal to the demo gods for my complicated setup here. Right, so let me slide this over so I can actually reach it. Alrighty, so let's try this. So my first claim, I'll just try making a sound here. Oh, there we go. So this is remember from math class, this is a sine wave. And a sine wave, right, this sort of perfect mathematical wave, has this kind of boring, perfect bell-like sound. And so that is the electricity coming off the synthesizer, which is driving the speakers, and it's also making that thing. So let me try. So what I want to do first off is just talk about what are the properties of a signal like that. And sometimes I'll use the word signal. That's kind of the term for this sort of data that I want to play around with. Or I might use the word wave. Those are sort of synonymous here. But really what I'm talking about here is signals. I'm going to talk about some of the qualities that signals have. The first quality I'll talk about is frequency. So this is kind of a low note. And so remember what I said with the oscilloscope is that it grabs a wave, and then it shows it to you again maybe 1/100th of a second later or whatever, or maybe 1/10th of a second later. So those variations in pressure, that's actually maybe 100 per second, something like that. And we're just seeing it very zoomed in. So the width of the screen in this case, I think, is 1/100th of a second across. And so really that's varying very quickly. And so most human speech, things like that, they tend to be in the range 50 cycles per second up to maybe 20,000 cycles per second. All right, so the first quality I want to talk about, and I just used the phrase cycles per second, but I never explained it, is frequency. So if I go up to something where there's more, and we're going to say this is more cycles per second. How many ups and downs do we pack into what did I say this was, 1/100th of a second? So when there's more in there, that's what you think of as higher, right? You have a note which is higher or lower, whatever. Also, this is higher, so it's going to is this kind of irritating? Okay, sorry, we'll go back down. All the dogs are going to leave the building. So that's what frequency is. That you have just a greater number of cycles per second. And there's actually, I'm going to go, we'll just talk about music a little bit. So when you go up 1 octave, so that's C to this one, what you think of as kind of a natural, it sounds right progression, that's exactly a doubling. So if you look at the number of cycles there, and I go up an octave, it's exactly a factor of 2, and we could go up into the dog range, but I won't. All right, so that's one quality of signal, of sound. Another quality, which is kind of obvious, is official vocabulary word, is amplitude. So in a very analog sense, the height that is going up and down corresponds to how big the pressure wave is, right? How hard is the speaker, the synthesizer, pushing on the air? So if I were to just turn it down, it just goes down. So that's what loud and soft is. Loud is just, in the analog sense here, just going out a little harder. So this leaves me with the most kind of baffling quality, which is called timbre. And that just refers to the shape of the wave, the little curlicues, whatever. And the sine wave is there's no timbre. It's just the most vanilla sound possible. So I'm going to switch the synthesizer to do cheesy pan flute sound. And what you see, I don't know if you can tell, that's the same cycles per second I was doing before. It's actually the same frequency. It's the same note, but it has this flute timbre on it, all the little curly cues and stuff on it. And what is amazing is how the brain, that's what your brain is getting. Those little curly cues and bumps and wiggles and God knows what. And your brain takes that in, and what it hears is flute. But then when it hears this one, it's like, oh yeah, sine wave. And well, that's a little bit amazing to me. Or certainly when we look at it visually, just as pixels, it's sort of, yeah, I have newfound respect for the ear and the brain. Really the brain, obviously the brain. The brain helps out there. All right, so what do we have there? Frequency, amplitude, timbre. That's just like classic stuff to know about these sort of signals. All right, so what I want to talk about is another question about how sound works. And I'll go back to my oscilloscope here, which is there's just one air. Like in this room, there's one body of air, and all the sounds in here, basically me talking and you all clickety-clacketing, like surfing the web or paying attention or whatever, it's all sharing the one air. And so the question I want to get at is, well, how is it, what happens if multiple sounds are going on in the air at the same time? Right? If there's someone's talking, and then there's a low note and a high note, and you can model, oh, well, maybe they just sort of obliterate each other, but that's not true. Really, you can hear, obviously, you can hear multiple things at the same time. And so I want to get a little bit is like, how does that work? How do multiple sounds fit into the one air? And so I'm going to do that by playing multiple notes at one time. All right, so I'm going to start off with, okay, yes, we've seen this one enough times, my low note, the sine wave. So what would happen if I played that one and, let's say, this one at the same time? And I'll tell you, I'll tell you, and then we'll look at it. The answer is addition. The pressure waves add on top of each other. So there might be one place where the one wave is kind of high and the other wave is also kind of high, so then they would add together and make it like even higher. And there might be other places where one's kind of high and the other one's kind of low, and so it's just arithmetic. However they add together, they make this composite wave that has both sounds in it. And so we can, it just happens, this works out very neatly visually. So I'll start with the low one, and then here's the high one, and I'll just do them at the same time. Oh, well, it doesn't come out quite perfectly there. Let me try one even a little higher. So there's my low one. Yeah, this will show up better. There's my high one. If I do them at the same time, I don't know if you can kind of see, there's sort of, the low one is in there, but just mapped on top of it is this high one. All right, so I'd like everyone to just close your eyes for a second. Just humor me. All right, so now, just isolate. You can hear, just listen to the high note. Right? You can recognize there's a high note there, or if you ignore it, you can also hear that there's the low note. So, all right, so you can open your eyes. So looking back, your brain is just getting the signal, and this is the amazing part. Your brain gets that, and it can parse out the two sounds that are going into it. And that, this again gets at my sort of, I'm impressed with the brain, how it can like pull that stuff apart. All righty. So I'll show you there's a, if you wanted to sort of prove or show for yourself that it's just addition, you can actually do it with graph paper, where you could sort of graph this note, which is this one, and then you could graph the note that's just one octave higher, so this one and then this one, just 2x. And then with the graph paper, you could sort of add up the components, so where they're both high, make it high, and where they're both low, make it low. And what you'll find is that you get this sort of, this is the classical one octave apart shape. And so I'll leave that as an optional exercise, but you could sort of show that I'm not just making this up. All righty. So let me show you a couple other interesting facts about this summing together of sounds. There's sort of an eerie relationship between mathematics and sounds, and in particular sounds that sound good and sounds that don't sound good. And this is, I guess, the ancient Greeks were captivated by this, and it is kind of magical. So what you think of as a chord in music, what sounds good, is when the peaks and valleys of two different sounds that you're going to add together, they kind of match up. So for example, it's kind of obvious that if I take this note and then I exactly double the frequency, exactly double, then the peaks and the valleys are going to match up perfectly. And so in fact, those sound pretty good together. You can say, or that's what a chord is when mathematically it kind of divides evenly so the things match up. So we could look at the other side. Well, so wait, what sounds bad? And the way to get it to sound bad is to have one sound be, let's say, at 100 cycles per second. So that's the spacing of the peaks and valleys. And have another sound which is maybe 101 cycles per second. Just a little bit off. And what you'll find is then the peaks and the valleys, they almost never coincide. The thing is just staggered. It makes kind of a mess. And what's neat about that is that there's something in your brain. So here, like, there's a chord where they match up pretty well. But then I'm going to add on one where, like, it doesn't match. That's discord. And what's amazing is how, like, isn't that just bothering everyone? It's like, I'm not happy. And then if I just go up, I just go up a little bit so it matches, then like, that sounds good. So that's math, chord, and discord. All right, so let me show you, I want to talk about, we break it down. So that's just signal, waves, things like that. So let me bring this over to technology, and eventually I want to get at basically like how a CD player works. Or a CD player, I guess that's an antique. So we'll also talk about how MP3s work. So for starters, if I'm going to talk about analog versus digital, I first want to talk about analog briefly. And we talked about this a little bit with my violin example. So I'll talk about the original telephone system, the Alexander Graham Bell model. And I talked about analog a little bit before, so this very much follows that pattern. The way the original phone system worked is, we've got the person on the left there, and they speak, so they make pressure waves in the air, and it hits a microphone. And I'm not going into too much detail what a microphone does, but basically it has a little magnet arranged next to a diaphragm that can be pushed by the air. And so as the air moves the little diaphragm back and forth, it makes a little tiny electrical current. And so the result is, right, that's analog. It means when the air cone is pushed a little bit one way, it's going to make the electricity go a little bit one way. When the air cone goes the other way, the electricity is going to go a little bit the other way. And so we end up with this perfect, essentially what the microphone does is it's an analog translator. It translates from wave in air pressure over to little pattern of electricity in the wires. And that's the classic analog step. All right, so a telephone then takes the electricity, right, having transformed the signal into electricity, well, now it can go on the wires. And so it goes down the wires. Now, in reality, the electricity, the signal is so weak that there's going to be some amplification of the electricity. So transistors, we talked about before. So it goes down the wires, and eventually it gets to the other end, where it gets to a speaker. A speaker is just the reverse of a microphone. So the speaker takes in the electricity, and it has an arrangement of magnets and cones and whatever, so that then the electricity pushes the cone out or in a little bit, and so it basically recreates the pressure wave, and so then the sound comes out. So this is the original design of the telephone system, and what's funny is that, not you guys obviously, but your parents, people who actually have phones in their houses, the last mile of the phone system, it still works this way. Like once the standard was kind of set and everybody had all these zillions of phones out there, it was hard to just have some big switch day like, oh, phones should work differently. So this is sometimes called a network effect, which I'll probably talk about a little bit later. But yes, there's this tremendous inertia where the phone, even though the central office of the phone company now works completely differently, the end part is still compatible with like the way it's always been. All right, so that's your classic analog structure, which will exist mostly so we can make fun of it a little bit. All right, so what I want to talk about is noise, hiss. Like, how is it that analog doesn't sound so great? So I want you to imagine this signal. This is, I call someone up and I have this beautiful bell-like singing voice, and I just sing this like perfect sine wave, and I just want it to be enjoyed by the person at the other end of the phone. So what I'm going to do, well, so let's say I sing that into the microphone, and it's perfect. What comes out of the other end? Right, it goes down the wire, it goes through the microphone, down the wires, maybe it's amplified a little bit, and then it comes out the speaker on the other end. And the answer is, it doesn't come out looking like that. What happens is really there's a little bit of what we're going to call noise, a little bit of error. And I'm going to, this is just me drawing a model of error, but you can think of the error as sort of like fuzz around where the signal was supposed to be. And the sources of error are many, right? Well, maybe the microphone, the paper cone was a little rigid. I mean, it didn't quite flex perfectly for my beautiful singing. And then the magnet has certain electrical properties that kind of shape the pattern of electricity it can make. And then the wire has certain qualities where most of the signal goes through, but the shape of it kind of gets distorted by the wire. All electrical components do distort the shape a little bit as signal goes through there. And so what I get out of the other side, you can think of it as like, well, the signal, you can see the signal, but there's this, and then the term is noise. There's this noise kind of added on top of it. And I'll tell you, noise has a distinctive sound. You have all heard noise. Noise is the hiss. It's the kind of like, so think of analog technologies you've used, right? So if you ever had, did anyone here have like cassette tapes? Maybe you got them from your grandparents or something. Anyway, when you play back cassette tapes, mostly the music would be there, but if you turn it up loud enough or if there was a quiet section, then you'd hear this like, and that is exactly, it's the noise from the tape and the magnets, all these sort of various layers that the analog was going through, there's this noise added on top. So phones actually have this, because phones are this sort of comically old technology for that last mile. And so anyway, that's why Skype sounds so much better than actually using a phone. OK, so that's a problem. Other examples, I guess VHS tapes. Those are analog. So in that case, the hiss sort of shows up as, or pure hiss, pure noise in video is that snow look, where the pixels are just kind of randomly flashing between black and white and color and stuff. OK, so that's whatever, analog. You can do pretty well, but it's not great. Oh, AM radio. So I need to think of a technology you guys actually use that's analog. So that would be a project for the future. AM radio has a significant amount of hiss.